Hey.
Hey, Moses.
How are you?
You're here.
Yeah.
How are you?
Oh my goodness.
Seems like going through a lot of things, it seems like.
Yeah. I'm probably gonna quit the leadership program.
What program?
The leadership program.
Oh. Is it taking too much time? Is that what it is? Because you seem to be involved in it.
I am very involved in it, but it is. I haven't been able to focus on school to the degree that I need to be. So. Yeah.
Maybe we should go for a coffee or something.
We should do that. Yeah.
Yeah. Well, let me know when you're available.
Okay.
Let me see. Yeah. Yeah. Sometimes talking just helps. Yeah.
For sure.
Hello, Leah. Hello, Luke.
Good morning, guys.
You're coming from St. Louis or from home?
St. Louis. I intended to come back yesterday, but I failed to get up early enough.
Yeah, that's just totally.
Yeah.
All of us here, I think. 1, 2. Where am I? Oh, I am on the Moses. Yeah. 4. So we should be having one more raw. Michael. Hello, Jordan.
Hello.
Oh, while we're waiting for Michael, hopefully he doesn't take long. So, Jordan, next week we have our midterm 2, right? So I'm planning to have it in class, and what I can suggest to you is that, is it possible that exactly like this camera you have the choice to just take the exam with, make it sufficient. I mean, this is good enough, put it like that. Okay? The camera stays all the time. Just make it whatever is needed, right? So that should help you with that. Okay? And I think, because anyway, Khalid probably, if he takes the exam, he will probably have to do the same. So you have the choice, but you're welcome to come and take the class, take the exam here. That's up to you. That's just an option. But others, there's a bias, but others have, I'll say, come down. Okay?
Okay.
Okay. So Michael's. So there's homework 5. That is due October 1. It's Thursday. Yeah. And so that's Thursday, October 6th, which is Tuesday. Oh, no class. And on October 8th, we have the midterms. So it's slightly wrong place to not have the class, but that's what it is.
Is there a reason we don't have class?
It's name.
Okay. Oh, got it.
My reasons.
Okay.
Yeah. Nothing. It's not a school.
Not a holiday or anything.
Yeah, it's not a uniform.
Gotcha.
I think it's called just my course.
Okay.
So Monday and Tuesday.
Yeah, okay.
Involved in something. Yeah. And yeah, so on midterm 2, so there are a few, like since it's going to be in class, it's good to point out a few things. I plan on giving a question on cube root. This is again tentative plan, but that should help. It could be cube root of anything, and reference is, this is a very general reference, Cardano formula. A lot of literature on this, but it's kind of nice, but you should be able to, given the Cardano formula, you should be able to get the cube root. Notice cube root is 3 of them, and mostly the trick is to find which are the 3. So, and then of course we have Cauchy-Riemann condition. And there might be complex numbers itself. And since complex number is from this course, it's a reasonably early concept. I can go as much as I want to make it complicated. So there's not much preparation you can do, but at the same time, it means that you have an idea of complex number, especially the Argand diagram. Realizing importance of Argand diagram in there. And what we will be doing today, you should be able to, so suppose I give you an analytic function f, or visual inspection of analytic function. That means to say that if I give you the particular explicit function, then typically you use Cauchy-Riemann conditions to test whether it is analytic or not. But we also realize that it is not very useful because it is not a sufficient condition, it's only a necessary condition. So the only tool other than that you have is to visually inspect it, what you look for in an analytic function. And I had given you an exercise, I think, in the extra credit, I don't know, I think it was due today, where you were supposed to plot x cubed minus y cubed and something, I don't remember what exactly goes, which function goes, and to figure out what are the properties you look for. And hopefully, after we do today's lecture, there might be more insight into that. Okay. So that's again, very roughly what the questions could be. Probably there will be 4 to 5 questions. It depends on how big the 5th question could be. There is a chance that one of the questions might be take home. Rather than take home, what I do is that you bring it with you. That's another, or either way, it is. So I might open it many days before and then you bring it with you. Is that clear what I mean there? I think you have taken such an exam with me, Jordan, as Alia and Luke. What I mean is that one of the questions might be available before the exam. So that means to say about 4 or 5 days before the exam. And I might ask you to do it and bring it with you during the exam. So it is a take-home exam, but it is not after the exam, it is before the exam. Is that clear what I mean there? Yeah. So anyway, so we have a few more days before that, so that's just it. Okay. Any general points? Anything else you guys want to point out? Comments or anything? Michael is still not here. Okay, so We said that given a function, let's say complex function f, it could depend on z and z prime, or not z prime, right? Z star, right? Complex conjugate. That's the most general complex function you can write. But if it is not dependent on this, then there is a chance that there's a good chance that it is an analytic function. So we will just say f of z, where z is equal to x plus iy, where x and y is real. We showed that this can be written in terms of u of x comma y plus I times v of x comma y. So two-dimensional functions of real variable. And we said at least the requirement is the Cauchy-Riemann conditions that du by dx has to be equal to, like you can write it as a matrix to the mnemonic, but I think and du by dy is equal to minus of d by dx. Those are the Cauchy-Riemann conditions. But we said that yes, that's really necessary. But once it is satisfied, you really don't know, like, is it really still analytic? And especially if it is not analytic at a point or on a line, right? So those are the features we would like to test. So we want to have a more insight into this analytic function. Can we look at this u and v and say something about whether it is analytic or not? Especially because last time we said that if you know u, actually we know v also. So if it is analytic, knowing u pretty much describes v also. So then we say, okay, how do we figure this out? And one thing we did point out, in fact, Luke showed us, is that if you have this u and v to be a part of an analytic function, then the Laplacian of u is second partial derivative with respect to u plus square dy square of u. And this is equal to, one can use so this is d by dx of du by dx is dv by dy. And do this. And plus d by dy of du by dy is minus dv by dx. And then if we use the fact that it is these partial derivatives commute, then this is equal to 0. And that means to say this satisfies the Laplacian. And whenever the Laplacian comes in, we think of our electrostatics, and we have some insight of electrostatics, right? Electrostatics is, recall electrostatics. What are the equations governing electrostatics, by the way? Electrostatics, not the whole electrodynamics.
The first two Maxwell's equations.
Yes. First two, yeah. So del dotted with E is equal to rho over epsilon naught. Correct? And
Del dot B equals 0. Or
electrostatics, electric, not magnetic.
oh, got it. Yeah. Del cross E equals minus del by del B, or del B by del
Minus partial by partial.
partial T with respect to T.
Try again?
I can't even speak.
That's okay.
Partial B with respect to
I know what you're saying, but think again.
0.
0, because it's static.
Oh, okay.
Right?
Yeah.
So it's statics, right?
Of course.
So this is there. So whenever it's electrostatics, it's just these two equations. That's
Yeah.
it. So magnetism is completely decoupled.
Got it.
Right? That's why in the introductory physics, we never talk about magnetism. That's completely separate, right?
Got it.
And the moment something is del cross E, this implies that E is equal to, like, what is
The gradient.
the gradient of a scalar, right? That means if this is a force, you can write this as an energy, right? So electric field can be written as an electric potential only in this case, right? Otherwise, you need the other features. Momentum also comes in. Like force depends only on energy, only in a static situation, right? Otherwise, momentum comes in. We'll see that later, right? That's nice, but if this is the case, I can actually put that in here, right? Put this in here. So how about this? So this implies, substitute this in. This is negative del square of phi is equal to rho over epsilon naught. Right? So Laplacian of the electric potential is actually charge density. Right? So if someone were to tell you that the Laplacian of a quantity is 0, what do you infer?
There's
Yeah.
no charge density.
There is no charge density at that point.
Okay.
At that point, there is no charge. That much you can be sure. If this is electrostatics, but this is, I mean, if that is a Laplacian, it seems like that's electrostatic. The only difference here is that this is in 3 dimensions. This is in 2 dimensions. Right? We are talking about x and y here. So we are talking in 2 dimensions. And again, this is at a point. These are local quantities. Right? Pick a point you want and you ask, oh, is there a charge there or not? And that's all we have to look for. So think of electrostatics to do this visual inspection that we're going to proceed. So notice there is a significant analogy we are making. There is something called analytic function, a property of a complex function. And on the other side, we are talking about electrostatics, which is again a very constrained phenomenon. Notice this is not every field can be written as a potential. Electrostatics is a case when an electric field can be written as a potential. How many forces do you know whose potential energy, which can be written in terms of a potential energy, let's say?
You say that again.
Notice when I say del cross E is equal to 0, if I were to think of it as a force equation, this means that del cross F, just think of it as Q times E, right? Del cross the force is equal to 0 implies that the force can be written as a negative gradient of potential energy, right? And now you can, and that's called a conservative force. Whenever you can write a force in terms of a negative gradient of a potential energy, it's called a conservative force. It is independent of the path taken. And now I ask, how many forces do you know which are conservative? List them.
Hooke's law.
Hooke's law, yeah, great. Yeah. So it's a one dimension, or it doesn't have to be 1 dimension. Yeah, Hooke's law, great, yeah. And that's correct. I mean, why? Because potential energy. The moment you have a potential energy, it means that it is conservative, right? So there is a potential energy. If you take a derivative, you get this, right? What else? How many potential energies do you see in your undergraduate physics?
There's gravitational potential as well.
Gravitational, right? F is equal to mg, and you would say U is mgh. Right? That's if you're doing constant gravity, like you're on the surface of Earth. We can also say F is equal to g m1 m2 over r squared, and the potential energy associated with this g m1 m2 over r. Right? What else?
Uniform circular motion, is that like a centripetal acceleration, centripetal force? No. Okay.
I don't think so.
Okay. I'm just thinking of like.
That's first of all, it's dynamical and
Yeah.
Yeah, I would say no. Yeah, but think about it. Don't give it up just because I said no. Think about it. Is there something? Yeah, maybe. I don't see it.
Well, I was thinking like the gravitational force that, like there's a centrifugal acceleration in the orbit.
I would say dynamical equilibrium there. Yeah.
Mm-hmm.
Again, don't give up just because I said no, but think about it. Yeah, immediately I don't see it. Yeah, but I might be wrong. Any other potential energies you can think of?
Like entropy or something. That.
No, entropy is different, right? Entropy. Yeah, let's not even go there. Now, potential energy. Let's stick to that. Yeah. That's a whole new digression we can take.
Internal energy, you know?
Yes?
Like internal energy?
Can you give an expression? You cannot, right? You cannot.
I think we pretty much only deal with gravitation.
Yeah, exactly. That's all there is to it. There is electrostatics if you want.
Right.
There's GQ1, KQ1, K2 over R, and this is F is equal to K Q1, Q2. I think this force is minus over R squared. And that's it. I mean, even though you will say that standard model like weak interactions, strong interactions, and all have potential energies associated with it at a basic level, that's all there is to it. And that why I asked you guys to list it is that it's very rare. Right? Potential energies are very rare, and that's because analytic functions are very rare. Right? Like if I say that an analytic function is an extremely constrained function, and it's not easy to have such forces or conserved forces. That's my feel. If you find anything else, let me know. This is I think while teaching, I come up with this, and then I realized that it's only this many. Okay, so
I have a quick question.
Yes.
So is the general idea that, if the force only depends on a position and not on time or speeds or velocities?
No, that's not correct. For example, so in Lagrangian, you will see, so position, of course, matters a lot. Think of it this way. There is an energy, okay, which depends on, let's say, X in this case, correct? And now energy tries to minimize. That is all nature does. Energy tries to minimize, which is, if you use your calculus, is represented by the idea that derivative, if something is a minimum, derivative has to be equal to 0. So you say derivative is that force. If it is equal to 0, that's good. If it is not 0, it will try to make it 0. So force is a manifestation of the fact that energy tries to minimize itself. Okay? That's in terms of X. But now bring in a new variable. Usually a nice thing is u of x theta, right? Angle involved in there. And you can say, again, energy tries to be minimum with respect to any parameter, in this case theta, and this time you call it torque. Right? You think of energy depending on any quantity, let's say alpha. I don't even know what alpha is. If I know that it depends on some quantity like that alpha, and if it is dynamical, in the sense that alpha can be, like the system has the ability to change alpha, then again the system will try to minimize its energy. So that's alpha. And this, I don't know what it is, so I'll call it a generalized force. And in Lagrangian, you will, let's call it F, right? So this will be a generalized force with respect to the variable alpha. Right? Does that answer the question? So it doesn't have to be with respect to X, but it has to be dynamical. Dynamical in the sense the system should have the ability to choose its alpha. That means it can change its alpha. Like if if I force the particle to be along a line, so only X is dynamical. So Y is not dynamical because the system doesn't have a choice to pick its Y. Does that make sense?
Yeah, I guess I wasn't thinking in terms of like X. I was just thinking in terms of, you know, a force that depends only on the position, because then it's a conservative, you know, it's
Yeah, but it doesn't have to be X. So let's say there are not many dynamical variables. Yeah. Okay. Most of what we have done is with respect to position. In terms, it could be theta angular variables, but it's mostly X. The system is usually having a choice to have. Oh, that is one thing, right? Spin. Spin is not a position. If you have a particle that depends on some internal degree of freedom.
okay.
Spin, which is not dependent on position.
Yeah.
And again, if the system has a choice to pick that, it will try to minimize it. Does that help? So
That's actually a perfect example.
Yeah, that's right. Yeah, without, so it doesn't have to be position, but it will always have this feature in there. There will be a corresponding force that will manifest itself as. But better is nature just tries to minimize energy. That's all it knows. It's just trying to do that, and everything else is it seems like there is a force due to that reason. The only feature additional to this is the entropy that you mentioned. Energies try to minimize, and then entropy tries to be maximized. So there is a dilemma in there. So it picks. But most of the time, what we are doing it because we don't understand entropy so well. So we say we are doing systems where entropy is not being considered at all. So most of your graduate level books, unless you're doing thermodynamics, entropy never appears. Right? And mostly because I think that we don't have a very fundamental understanding of entropy. But that's my comment. Don't take it too far. Helps? Okay.
Yes, it does. The spin really helped mentioning that.
So yeah, so that's all a parallel thing there. But we are interested in Laplacian, right? Laplacian of U apparently is 0. And the same way Laplacian of V is 0. So Laplacian of V is 0. So let me not even write these details. All right. U is 0. V is equal to 0. And there's one more thing one can do. And maybe I should also point out when there are two things going on here. Sometimes we think of this as a complex plane, that this is X and this is Y. So this is a complex plane. And sometimes we think of it as just a real plane with X and Y as variables. In this case, this is Z. Z is X plus IY, right? And in this case, for example, a vector R is X times I plus Y times J. Right? This is a vector, a two-dimensional plane, and this is a complex plane, right? And multiplications and divisions have different features, and that even though addition and subtraction is the same. And whenever I'm talking about this gradient and other things, that's in this vector space, right? That's in this position space, because gradient here is I times d by dx plus j times. So when I say gradient here, my understanding is I'm in this point. So this is I hat d by dx plus j hat d by dy. Okay. So, and even though we jump around from one to the other, one should be careful what I mean. Okay, nice. Let's also do del of let's also do divergence of sorry, not divergence, right? Gradient of u is actually I hat du by dx plus j hat du by dy. Right. That's the gradient, right? That's what I mean by this is that. So remember, this is a function of u of xy. Think of this as potential. Like it will turn out that u actually is a potential in two-dimensional electrodynamics. And of y, so the gradient of not y, v. I hat dv by dx plus j hat dv by dy. Okay. So one can ask, what is divergence of u? Oh, okay, divergence. What is gradient of u? Think of u as a potential. Gradient of u will be some electric field then, right? If u is a potential, gradient will be an electric field associated with this potential. This is an electric field associated with V potential. And you can say what is their dot product, right? There are two electric fields, and you can ask for two vector fields, and you're asking what is the dot product of the two quantities. And let's evaluate that. So that's du by dx times dv by dx plus du by dy and dv by dy. But we are saying that these are analytic functions, so it satisfies Cauchy-Riemann conditions. So dv by dx is nothing but du by dy. Du by dx. This is du by dy with a negative sign. The next one is du by dy. dv by dy is nothing but du by dx. And that's also equal to 0. So that's another way of seeing the constraints. I said we want to, since Cauchy-Riemann is not a sufficient condition, so we want to do better, right? What else can we use to have a field for this functions? So that's your constraints. And with our electrostatics, we might be able to do more. So in electrostatics, if a point does not have a charge, that seems like at that point, that's analytic. That's one way of looking at it. How will you, if I give you the electric potential and electric field, how will you realize, or how will you know that there is a charge or not? Just by visual inspection. What's so special about an electric field at a point where there is a charge? Good. It's infinite, and visually speaking, how does it look like?
It diverges.
No, more than that. Field lines, let's say.
Radially outward.
Radially outward, right? At that point, so all of them seems to converge. Like divergence of the electric field is not 0. Right? It's actually non-zero. Divergence of electric field is this, right? Everywhere else, if you go outside the charge, it's 0, right? Only at that point it seems to be infinite, right? So that whole idea we can bring in. So we just have to say, do the divergence of this quantity and see, get the field lines, are they converging at that point? If they're converging, probably that's not analytic.
Okay.
Right? So that's going to be our visual field. So let's do some very simple.
When you say probably not,
most probably, yes. See, I'm being careful here in the sense, I don't know how much of this is a theorem, like how much of this has a loophole in it, put it like that.
Right. Well, those all satisfy Cauchy-Riemann conditions, which are necessary but not sufficient. Right?
Exactly.
So there's still the possibility.
Yeah. I would. Yeah.
So is there any way to correctly determine if a function is analytic across its entire domain? Or is it
So here is a
an educated guess based on
so that is a theorem. Again, so this is extra credit, right? So let's say this is extra credit. Find a function, find f of z, which is analytic everywhere on the complex plane. Is the question clear?
Yes.
Right. And does anyone know before? Yeah, or it doesn't exist. Okay. There's no analytic function which is analytic everywhere. If it is, then it's a constant function. Okay, so don't ask me to prove it. Okay, so that should give a feel for it. So that's another way of looking at, like earlier I said, can you get a function without creases, right? All this analytic function has to do a lot with creases. I mean, it's very hard to build a function which has no, and it shouldn't go to infinity either everywhere. That's also a feature. Right? So the point is, and it also has this feature that this complex plane, when you say, again, I don't have a complete grasp on this. So there is this x and y. So this is a complex plane now, right? And the same thing with the real plane also. We can ask, when I go in here, keep going on to the right, I encounter a point which is called the plus infinity, right? When I keep walking to the left, I encounter another point which is minus infinity. If I keep walking along the y-axis, I get plus I infinity, and there's a minus I infinity. Okay. Now, what is the difference between all these three? Are these all different points, or are they identical? Okay. So, again, when I read literature, there are statements made like these are all for an analytic function. They're very, yeah, let me not say anything beyond it. Look it up. Okay. Understand, yeah, try to understand the boundary of it. Yeah. Interpret the boundary of a complex plane. Again, it should be for analytic functions. That means to say the value of the function as you go around to infinity. How is that? Have you guys heard of stereographic projections?
No, I don't think so.
Yeah, okay. So the idea is the following. Often you don't know, I mean, infinity is very hard to have an interpretation, right? Very close to it. If all the features of a function are at infinity, at large distances, you don't like that. So you want to bring it closer. So the way one would do that is that, let's say there is a x and you make a circle. One of the ways is that you make a one-to-one mapping in the following, actually not this way, start from here. So this point corresponds to this. This point corresponds to this. This point corresponds to this, and so on. Right? So there is a mapping you can build. So whatever is the value of the function here, it approaches and closer comes here. And the point from the other side similarly comes and reaches here. So the idea is that if it is if the function has to have isotropic derivative, so all these functions at infinity should have very similar properties, especially if we can stereographically project it to this point. So actually all those, like if it's a plane, all those points should behave in a certain manner as they come closer and closer on a circle. So in that sense, all those infinities, that boundary has a huge constraint on it. That's just very hand-wavingly I'm saying, but that should give you a thought on what I am trying to hint at. I personally don't have a very good handle on it.
You could do a stereographic mapping for both X and Y.
Exactly. Yeah. So that's roughly like very hand-wavingly, but hopefully,
Okay.
if you guys get motivated enough, you can take it. So things get very geometric at this point because we don't have a concrete way of putting things.
So my question quickly is that the only one that I wouldn't understand is if you drew the straight line itself, how you would map the point on the bottom at x equals 0 to the point at the top.
Not on the top, right? That will be at the bottom itself. So if it's a straight line itself, right? This point is here.
Mm-hmm.
This point is here, right? So this point goes here. This point goes here. If this point goes here. Does that help?
Yeah, I guess I'm not getting the map between that point and the point at the top, basically.
Oh, at the top. No, this point is here. This point is this point on a circle.
Okay.
So the top point will be at infinity.
Okay.
Did I? Maybe not.
Yeah, I think you said it correctly. I just visually, I guess is.
Yeah. So this is called. I mean, it doesn't have to be this. You can take any surface, but usually it is a circle. So this is basically stereographic projection. It is on a circle to a plane, but imagine any other dimension, sometimes. Why do you call it stereographic? This is how a movie works, right? I mean, you see it on a two-dimensional plane, but it's a three-dimensional. You basically project everything, every vector on a two-dimensional plane. Take a three-dimensional vector and project it on a two-dimensional plane. That's basically a movie that we see around. Usually there is a transformation like this. Here, the transformation is this geometry that I'm talking about. So you can actually get this transformation from this x to angle theta here. So similarly, think of any transformation like that, and that's basically a movie. And usually that is decided by the light source. So there is a source of light, and you actually project it along that line. Very vaguely speaking, but you can make it concrete, very concrete. It's I never explored it too much, but well understood. And in movie theaters, especially graphics, they use it a lot. Okay, with all this visual pictures in mind, let's do an example, right? So this is our hope we can. And remember that big difference between electrostatics and this is that this is two-dimensional. But we know two-dimensional electrostatics. What is a point charge in 2 dimensions? What's the analog of a point charge in 2 dimensions? Maybe a line, right? A line charge. If you have a charge that is elongated, very long line, then it's practically speaking, we are in 2 dimensions. So all lines which are all parallel to each other moving around. So that's electrodynamics in 2 dimensions if you want, right? Or collapse the 3rd dimension because there is no information in the 3rd dimension. Everything is the same. So that's an idea. Okay. Okay. So with those ideas, let's do an example. Right? The simplest example of an analytic function, very simplest is z itself. Right? So f of z F is Z. I think it cannot get simpler than that. And let's see what does this mean. Right? So of course this is X plus IY. And actually, let me switch goals. More space. So, example. And F is equal to Z. And Z is equal to X plus I Y. So what is our U? That's X, correct? U is X and B is Y. And we know that U is a potential, B is a potential because there's del square U. We immediately know that del square U is equal to 0, which you can test immediately, right? Second derivative of X is 0. And same thing with second derivative of B is equal to 0. And they are also normal to each other. Like there is an electric field associated with this, there is an electric field associated with this. They're actually normal. You can think of it as magnet. One is electromagnetic, electric and magnetic. But not a good idea to compare with magnetism because magnetic fields are not really, like they don't have a source. Right? But in statics, especially if it doesn't have a source, I think it's actually the same. Right? So then it's a effect. But okay, so that's our understanding. So let's see. Let's realize this, or let's draw this. So let me call this. Let's work with U. Okay, so let me call it a realization. Right. So I want to construct this function in a sense, starting with U. So realization 1. So U is equal to X. Let me understand that. So this is U is equal to, so we are talking about electric potential, which is having U equal to X as the potential. So let's ask when is U equal to 0? So U equal to 0 means X is equal to 0. So X equal to 0 means this one, right? So that's your line corresponding to X equal to 0. So that's U equal to 0. U equal to 1, let us say, will be a line here. So I say U equal to a constant, and it is immediately clear that these are your equipotential lines. I think that's what they're called. Right? If the electric potential is the same. So what configuration of charges has equipotential lines like this? If I have to ask you guys.
Just a line charge, right? Like we were saying.
Line charge is coming out, right? So for example, line charge in 2 dimensions is coming out of it. So it's
I thought we were saying the line charge is in the long X equals 0.
No, then like one should ask, so this is XY plane. When I said this is electrostatics in 2 dimensions, the charge itself, the line has to be coming out of it because Z does not come into picture at all. So this is basically a point charge will be like this, right? That's a point charge, right? But the 3rd dimension is coming out from here, so you want to kill that. So that's, you say that it's everything is the same in Z. So there is no physics in there. If that makes sense.
Well,
It's like saying, okay, so for example, if there were two plates, like this is a
A
plate.
parallel plate capacitor, I guess, would be like that, right? Not the field, but the equipotential lines.
Yes, that's correct. So this is a parallel plate. Yeah. I'll come back to that. So I was just saying, if you have two planes, now let us say, so this is going to infinity. So one has to imagine this to be infinity if necessary. Right? And then I say, whatever happens, and there's nothing else. Absolutely, there is no symmetry. If I put a charge here, then it breaks the symmetry. Right? Now, let's say there's two plates. Now you're standing here. You're sleeping. One of your friend comes and moves you from there to here. Will you know? You cannot, because of symmetry. There is no way you can figure that out. Right? So Z is practically not there. So who cares for Z? Just make it a plane. So kill all this, right? And this is just a point, right? Not a point now. These
Lines,
lines, right?
Yeah.
So, but the point is, Z direction was like if it is a plane, actually there's a whole plane, right?
Yeah.
So it doesn't matter where you are, so you can kill that symmetry. But now you're saying the same thing in XY plane, right? I want to kill the Z direction. So what I want to do is whatever is there here, I extended it to the third dimension so that there is no information.
Okay, yeah.
The point charge, if I extend it to both X, Z plus Z and minus Z direction. But here we are saying equipotential lines, for example, parallel plates. I think what Jordan pointed out, that if you have a plate, electric or its equipotential lines will be like this. I'm not talking about electric field because, so let's say, I think it's clear. The electric field lines will be like this, right, for a plate. Equipotential lines are perpendicular to that. So that's your plane. So think of this as a plate, but two-dimensional, so it is a line in a sense. But this is not a line charge. It's a conducting plate. Conducting plate.
So we do have to kind of assume that the Z direction, it does extend to infinity in the Z direction as well.
Yes,
Yeah.
yes, yeah. You want to have the whole thing extended there.
Yeah.
But then, since we are not going to keep that this is electrodynamics in two dimensions, so kill the Z right away. So then the question comes, what is the point charge? For example, in 3 dimensions, a point charge has this as the electric potential, right? Agreed? That's UV. Right? What is the point charge for a 2-dimensional charge? Like a point charge in 2 dimensions, which, as you guys said, is a line charge in 3 dimensions. What is the electric potential due to a line charge? Is that clear what I mean?
Yeah, would it just be Q over X for a line charge?
No, remember that actually, so there's more than, one would ask, where is the geometry coming in, right? So this is electric field. Again, it has a direction, right? So this is 1 over 4 pi epsilon naught.
Is it 1 over 2 pi?
Yeah. What is 1 over 2 pi? Yeah. What is it?
It's the same as for like an infinitely long. Is that right? Like a charge.
Okay, let me build it. Okay.
Charged wire, basically.
If you have an electric field like this, so there is a point charge, right? Gauss's law tells you that E dotted with ds, right, has to capture this charge. And 4 pi r square comes from here, right? If you remember, there's a 1 over r square, right? Just arguing and waving it. R square cancels, and there is a charge that shows up there, constant. Do you know what I'm talking about? Like I'm not doing the details here.
Well, wouldn't 4 pi r squared come from the differential area?
Yes. Okay.
And aren't we talking about differential line? Yeah.
So there is a point charge here. right?
Oh, yes. I get
And
it.
it has an electric field line.
Yeah.
It seems like I just told you what your electric field line is. But I'm saying, no, this is more than that. Your geometry decided that. Your 3 dimensions of your space, the 3 decided that R square. Why is that? Because independent of what I choose my surface, this radius could have been anything, right? My E dot ds has to come out to point charge Q here. I don't have a choice there. But electric field or ds here, area, has a 4 pi R square. This R square comes from the area.
Yes.
Right?
When I saw ds, I thought it was a line.
No, that's what you're trying to do.
Yeah,
probably. Yeah.
Yeah.
No, so this is area or
Okay.
dA, right? I think I typically write dA. A. So that's 4 pi R square. This has to be having an R square. No choice there. If you want to cancel those and get a Q there. So notice how the 3 dimensions, the area decided this. This R square is not a coincidence. It's because our space is 3 dimensional. Right? That's a surface area of a sphere that you can build. Now let's say that I'm in 2 dimensions, right? I'm in 2 dimensions. Again, think of an electric field which is going outwards and do the same physics. Right? But I am now in 2 dimensions, so this is a circle. Right? This is a circle, so that means this area is 2 pi r. So this has to be 1 over r. Whatever is the coefficient, I don't care. But this has to be 1 over r if I were to cancel that, invariably which circle I pick. So electric field in 2 dimensions has to be 1 over r, except some coefficients, and it has to be rho hat. And rho hat is the cylindrical polar. If electric field is 1 over r, what is electric potential going to be?
It's a constant for the
What's the connection between these two?
It's a gradient, so
Yeah.
But the natural log of
Yeah.
R.
Natural log of, right? So log of r. In fact, that's for a, if you do this for a, if you remember your elementary electrodynamics for a line charge, it comes out to be log of r. Actually, it is log of x squared plus y squared, right? That's how you write it. You don't have to write square root even, and that is 2 pi. If you want this, all this, I think that is 2 pi epsilon naught, and that is a factor, so 4 pi. And there's a factor of 2 there. And since it's a line charge, you will say this is lambda now. Right? Lambda is charge per unit length. So in this case, point charge is log of C. We'll come back to that. It might be your exam question, one of like the 5th question that becomes, so what does it mean to say point charge? So there's nice interpretations there. We'll come, first let's do some simple things. Okay, we'll come back. But because there things diverge, as you said, lines come together, so there's more features in that. Let's make it simple.
Okay.
Okay. Okay, so hopefully that, by the way, we extend that, right? So that's 3 dimensions, 2 dimensions, what is 1 dimension?
Not sure how you could have a 1 dimension.
No, 1 dimension is that. Oh, no, it's possible. And do this again, right? So this is a 3-dimensional sphere. That's a 2-dimensional, or whatever thing do you call mathematically call it. So this is a circle, right? If it's a 1-dimensional, circle is just 2 points, right? And that's the origin, let's say, right? So everything is on a line now, right? And now 1 over r squared, 1 over r. Here the geometry plays bigger role. Like think of a point becoming a line will become a plane. What's the electric field you applying?
Oh, so there's no pi's now. You just have 1/1/2. Is that right?
Yeah, you're saying it correct. Yeah. 1/2
Well, you just have one
charge per unit area, so it's a constant.
your Q or whatever. So your sigma, I think, is what they use.
Sigma over epsilon naught, but the main idea is that distance dependent, right? 1/r squared, 1/r. This is constant. Constant times z hat. So that's the z hat version. Correct. So what's your v? Derivative of what is a constant?
X.
Yes, so it's just x.
Yeah.
X. There's only one dimension here, so that's just x. And remember, potentials are always off by a constant, right? Plus a constant. Right? This is also plus a constant, and you usually pick that constant to be 0 at infinity, right? So you say it's 0 at infinity. This is also 0 at infinity. Here things change a little. Now it's not 0 at infinity, so that's somewhere else. So that is a huge divergent piece here. So it's not very obvious capital. So that's a length dependent quantity in there. But I mean, yeah. So should I go there? No, that's not good. There's a divergence. So this is not very useful. There's a logarithmic divergence. So. Or yeah, extra credit, right? Extra credit. Think about what is the electric potential for a planar geometry. So there is a divergence associated with it, which is not easy to capture. Like, but it is not that, not really. Okay. Okay. So with all that, let me at least finish this. Okay. So now that's U. So this is clear, right? This is equipotential lines. Now that's okay. Good. Let's do grid. If I have to do electric field lines, right now I want to imagine this has electric field lines associated with that. I can of course think of, since I know planar, a plate, conducting plate that too, they're going to be going outward, but let's do algebraically, right? Electric field associated with this is negative gradient of U, right? So this is negative I hat d by dx, negative j hat d by dy of x, right? And that's just negative I, that's it. Right? And that means to say that electric field lines are all pulsating in the negative direction, right? Why in the negative direction? Because electric field lines go from, remember, negative energy is minimized, right? The energy is the lowest when x is negative, right? Negative infinity is the lowest. Negative numbers are smaller than positive numbers. So electric field always points from higher potential to a lower potential. So these are higher potential, and U equal to 0, U equal to +1, let's say. This is U equal to +1, and this is U equal to -1. Okay, that's for electric field lines. Suppose I really want to have, like, it's very clear that visually electric field lines are pointing in the direction. What is the equations controlling the electric field lines? How do you get equation of a line, the field lines, from an electric field itself? Is the question clear?
Yeah.
So for example, 1/r squared, right? That's electric field lines. We know that it is really the outward. We have sort of studied this so many times. But algebraically, how do you get that?
Test charge?
The test charge, but that's not algebraic, right? That's visual.
Right.
Will you ask the question one more time?
if I give you an electric field, like for example, this is an electric field, right? I know that they're all pointing in towards the left, right? But that means that should tell me that field lines should have y is equal to a constant, right? That's my field lines, right? How do I derive that from here? Is that clear what I mean?
I think so, yeah.
So the way you will go about is the equation of a line, like line element, let's say, is ds, right, is equal to dx in the I direction plus dy in the j direction plus dz in the k direction, but we're doing two directions. I want, so given any, if I tell you that this represents an electric field line, what is electric field at this point? It is tangent to that, at least directionally. It's tangent to that. So electric field lines are tangent to the field lines, electric field lines at that particular point. Right? So since it is a tangent, that means given that line, this has to be proportional to Ex. So if there is an electric field, Ex I plus Ey j. Now to get the field lines, since they're tangent, the slope of this has to be equal to the slope of that line. Right? So I say that slope of this line is dy by dx. So you can say dx over dx. The ratio of these two should be exactly equal to the ratio of these two. That's how you'll capture the electric field lines on a line. Okay. So we want to get this x and y that have dx and dy like this. Right? So we know ex and ey here. What is it? -1, right? For us, it is -1. So we are looking at dx over -1 is equal to dy over +1. Oh, sorry, +0. I don't want to say it's infinity that kind of kills it. So let's rewrite this equation as ey dx is equal to ex dy. Is that clear what I'm doing now?
Yeah, it is.
Okay, again, the idea is that electric field lines, by definition, are lines which have their slope exactly equal to the slope of the electric field at that point, like as a direction of the electric field. It's decided by the slope, correct? So the slope here is Ey over Ex if you want. Slope here is dy by dx. These two have to be the same. That's all we mean by electric field lines from an electric field, right? So then I ask, okay, which equation, which y as a function of x is that quantity? So I have to solve this differential equation. And that's what we're doing basically. So Ey is 0, so basically we are doing dy by dx is equal to 0.
Yeah.
Correct? And which is what is there if you realize that this is 0 times dx is equal to minus dy. Right? So that means to say dy is equal to 0. That means y is equal to constant. Right? Which is what we argue. Y equal to constant is these lines, right? So that's your field lines. And they're pointing this way. That's your field lines. Is that clear? It makes sense. Equipotential lines, they're perpendicular, which is what this is, right? Or, yeah, not yet, right? So it seems like electric field lines are perpendicular to the electric potential. So a natural candidate for this electric field should be your V. Even though I didn't begin with V at all, there was no V there to begin with. But we know that this is perpendicular to that. right? Maybe, right? So, but we'll come to that again, right? So it seems like a realization of this analytic function is what? A conducting line. If I want electrostatics, just place a conductor and ground it. It's necessary that you ground it. You don't want to put a voltage on it. Ground it, measure your equipotential lines, right? Wherever, so if you want to do a lab experiment, you just put equipotential lines and measure your U. It'll come out to be U equal to X, right? Once you know U equal to X, you can get your V using your Cauchy-Riemann conditions, and you have an analytic function. Right? That's a realization of this analytic function. Very simple at this point. It seems like trivial almost. It's just slightly more complex. Let's do a second realization before I proceed. So that could be another realization of this. Right? Who says I should start with U? I can start with V. So let's do V is equal to Y. Again, do the same thing. V is equal to Y. Let's say V equal to 0. That means Y is equal to 0. Y is equal to 0 is this line, right? I'll place a conducting plane there. This is V equal to 0. Think of it as an electric potential. So this is a conducting plane. Right? Again, think of it as having some charges. This will be your equipotential lines, V equal to 0, V equal to so on, higher to lower. So field lines should be going this way. So it's almost immediate, right? So that's V is equal to Y. Electric field due to this Y. This is a new configuration, notice. If E is equal to Y is negative J. Negative J. This time that goes down. I can get the electric field lines, do exactly the same thing, dx over 0. This time, this is equal to dy equal to -1. This implies dx is equal to a constant. That means x is equal to, no, dx is equal to 0. Dx is equal to 0, so x is equal to a constant. And x equal to constant is these are your field lines, and they're going down because they go from higher potential to a lower potential. That's your field lines. So it seems like the electric potential and electric field are, they take the jobs interchangeably. So these are called conjugate functions. And this whole property was realized, I think we observed this in 1870s probably. Maybe 1880s or something around that. I don't know who exactly did that, but there was a lot of discussion. I mean, usually the textbooks of 1880s, or if you go by 1900, the classic textbook like what Lawrence wrote or Smith wrote, there were a classic textbook of those times. They all covered a good bit of chapters on this, but all the modern textbooks seem to have removed this. So look it up. It is less popular these days, like in the standard textbooks, but I think everyone knows it. It's not that no one knows it. Most of the people, especially in that complex variable, everyone knows it. Okay, so let's do a little more complicated, right? So Z turned out to be too simple. After you realize it, it's simple, but a good exercise to do. And let's now do the next one, right? So next is Z squared. Maybe that's a simpler one. Maybe there are more simpler ones, but let's say Z squared.
It is 1050.
Oh, it is 1050. Oh.
Yeah.
Yeah, no, let's stop here.
I can stay for.
No, I should stop. Thank you. I should start a good habit. I didn't realize. I thought I had 10 more minutes. Okay. Yeah, no, let's stop. Good point. Yeah, we have another lecture also, right? So we'll do that. And I'll do 2 more examples on this. And what I plan to, or at least today morning, I was thinking that the point charge I will give it as an exam, but I maybe do something of that in the, yeah, the point charge I will give it as an, do it in the lecture. Then the next version of a charge is a dipole, right? So dipole has good properties in this case. So it's kind of, if you have a geometric feel for this, it's kind of nice. So, but let me stop. Like, you have enough things to talk about. And yeah, thank you for pointing that out. Yeah. Okay, good. Enjoy, guys.
Thank you.
Yeah, thanks.
See you guys. Well,
Yeah.
Thursday.
Put you on the camera.
Hey, Moses.
Hey, how's it going?
Pretty good.
I like your shaved head. Looks good.
At some point every year, I get tired of messing with my hair. And my wife likes me with hair, but you know, it just gets in your face, and you get.
Yeah. My hair drives me crazy.
Yeah, so
I still haven't buzzed mine off.
it's a nice feeling. It really
Yeah,
is.
I'm sure it is.
Since I have to get up really early in the mornings, you know, if I take a shower in the evening, then I don't have to worry about showering in the morning. But before I would have to, because my hair would be everywhere from my pillow, you know.
Yeah.
So just makes it easy to say, I can just shower in the evening, I'm clean when I wake up, and then get my day started so I can sleep into the very last moment possible.
Yeah. Yeah, less to deal with, that's for sure.
Yeah, I enjoy it.
Yeah.
Usually my wife says, well, you should, for whatever reason, I always shave my head like in the fall, like going towards winter time. And she always questions me for that because my head is actually just so white because it's gotten actually no sun. And so I just, the color of my arms and the color of my head are just two different things. You know, I'm not trying to find a girlfriend or anything. You know, I already have a wife, so it shouldn't be a big problem, right?
You should look good for your wife, though. That's important.
Yeah, yeah. I just tease her. It just happens to be when I usually do it. Although it would make more sense if I did it in the summer because sweat and getting a little color on my head would probably be beneficial for a shaved head. But
perhaps, but you are protecting yourself against the sun as well.
That's true. There you go. That's
my dad's bald and he gets sunburns on the top of his head. So I mean, there's a plus to having some hair for sure.
Yeah, yeah. Well, and it's a good start because if I ever actually do go bald, then I don't have to. You know, I already know what my head shape looks like, and it's not particularly good, but you know, it is what it is. So. Alrighty.
Okay.
I'll talk to you guys later.
All right. That sounds good.
Yeah. Okay, I'll disconnect.